The purpose of this lab is to observe the changing position of an object with a constant velocity and compare this observation with a model that predicts the position of the object. The object I observed for this lab was an expo marker. I analyzed its movement and position using Tracker and created a computational model of its position using GlowScript. The computational model applies the velocity update version of Newton's second law, as well as the position update formula to predict the future position of the expo marker. The fundamental principle applied in this lab is Newton's second law, which is also known as the momentum principle. Newton's second law relates the net interaction between system and surroundings to the observed motion of the system. To elaborate on this, Newton's second law states that an object that has zero net interactions will maintain a constant velocity motion. The velocity update formula, which I used in creating a computational model of the expo marker's position, can be derived from Newton's second law. After writing in terms of final and initial momentum, I divided both sides of this equation by mass. Then, adding initial to both sides results in the velocity update formula. The procedure for this lab was to record a video of an object moving with constant velocity motion, then analyze the video in Tracker, and from there, construct a computational model to predict and display the object's position. Here is a clip of an expo marker rolling at a constant velocity that I analyzed in Tracker. The expo marker is the system in this video, and everything else are the surroundings. I chose to orient the positive x-axis to the right and the positive y-axis is up. For each frame of the video, which represents one time interval, I placed a pointer on the center of mass of the expo marker, and these are the red circles that you see on the screen. Doing this generated a graph of the marker's position at each time interval. After tracing each change in position, I found the marker's initial velocity using the first two positions and corresponding time steps. This is the velocity I used to create the computational model, and it is 0.5200 meters per second. Here is a screenshot of the code for the computational model I created. First, I updated the velocity and position equations to be the velocity and position update formulas, which are velocity equals velocity plus net force divided by mass times delta t, and position equals position plus velocity times delta t. Then, I changed the net force to be the zero vector since I am assuming the expo marker moves with constant velocity, and as previously mentioned, an object moving at a constant velocity has a zero net force. Then, I changed the time step delta t to match the time steps of the recorded data from Tracker. Lastly, I updated the object's mass to match that of the expo marker, and I updated its initial velocity to match the velocity I computed from the Tracker data. Here, I am assuming the expo marker moves with a constant velocity throughout the video. This program generated a chart of where the object's position should be at increasing times when it has a constant velocity of 0.5200 meters per second. Here is a graph comparing the data extracted from the observed and model position versus time graphs. You can see that the line representing the observed position continually diverges from the model little by little until towards the end of the observed positions. This is around 1 second when they briefly line up again. There are a few reasons that could explain this inconsistency. Because the observed position diverges from the model and is higher than predicted by the model, it is possible that the force of the person initially pushing the marker was larger in magnitude than that of any other forces acting on the object when it began its motion. The marker likely had some magnitude of a friction force acting on it due to it sliding on a table, but this should have resulted in the observed position being lower than the model. Another thing is that I could have made a mistake when placing the center of mass on the expo marker for each video frame. To conclude this lab, I'll talk about how my results could have differed and the forces acting on the object throughout the video. If the negative and positive x-axes were interchanged, the results would be different because they would be negative. The graph of the observed and model positions would have slopes of the same magnitude but with a negative sign, so they would be pointing down. It is not possible to determine every force acting on the expo marker to give a zero net force. While rolling on the table, the expo marker was presumably acted upon by friction forces and possible air resistance. There should have also been a weight force pulling on the marker, one from the table that's pushing it, and other forces that all add up to be the same magnitude as the push that initially set the marker into motion. So in conclusion, we cannot determine the total number of forces acting on the expo marker to give it a zero net force. This is all I have. Thank you.